Um, so I want to talk about network dynamics, and I'll just start by motivating kind of why I thought I would say something. And I think my big motivation is people like ODEs. So it's a kind of uncomfortable fact, right, for probabilists. But an awfully large proportion of applied... but an awful lot of applied work in epidemic modelling is based on sets of differential equations. And I think that's just sort of inescapable. And so I guess we go around with this kind of heuristic picture of an epidemic, and it does something stochastic here and here. But despite being dominated by stochastic effects, it's possible to get asymptotic results based on a fully kind of principled stochastic approach for early and late behaviour of an epidemic. And that's not what I'm expert in particularly. And what I'm interested in is kind of this bit here, where the dynamics are really dominated by nonlinear effects, so you can't linearise the system in any way. But you kind of lost a lot of the noise. Not all of the noise, as I'll go on to say, but you're kind of dominated by the nonlinear trend. And like I said, I think this, my motivation really is that this area is, when people are doing ODEs, they're normally assuming there's no kind of underlying network or household structure. And so what I want to talk about is ways of getting sets of ODEs, relatively low dimensional sets of ODEs that attempt to capture the way that network structure changes this temporal or transient behaviour of the epidemic. And in particular, the relation, I guess one of the things you might want out of that is what's the relationship between the peak height and time, which is kind of a key quantity for intervening during pandemics or outbreaks. Sometimes you want to know when it's going to peak and how high. That turns out to be very, very sensitive to network structure, even if you condition on R naught or early behaviour. Okay, and I'm going to my other aim is to talk through it sort of slowly enough that people get something out of something of the kind of general approaches that are now coming online. Okay, so the underlying model. So you've got a random variable, and it's going to tend to be SIR, but later I'll talk about SIS with contact tracing. And so this index I runs over all of the big N individuals in the population. And so what I mean by kind of network structure is that in the most general case, individual I changes its state from susceptible to infectious. So each individual just recovers constantly, but you have to, in the most general case, keep track of every individual, and every individual has a different kind of weight of interaction between them. And so the interpretation of this is that individuals I and J have in general got a weighted dynamic so you could draw a kind of weighted dynamic network. That would be one way of interpreting these different rates. Although the general mathematical frameworks call this kind of interacting particle system, where you start off defining rates between individuals like this.
So interpreting that IJ as an indicator function there?
No. So because it's the level of individuals, the Tij is a so it maps from time and the set of all individuals onto. I guess they also have to be. So it's time varying matrix, real value matrix. In the most general case, and in the most general case, you can't do anything. You have to simulate, right?
And the IJ.
The IJ is one.
No, that's not an indicator function. No, sorry. So xi are the random variables. So this is just a way of defining what the rates are of the. So this rate means that the probability of going, the marginal probability that the random variables are non-independent, which is what makes it tricky to define carefully. This means the marginal probability of going from I being S to I being.
The
IJ in that second sum, that should be.
Given that it's
yes, it should be. Yeah, sorry, no, that's a typo. Sorry, yeah. Yes, of course. Sorry, yeah. Yes, that is right. No. So because these aren't indicator functions, that's just a way of defining it. That needs to be an indicator. Yep. Okay. So the full equations are 3n dimensional. And the traditional approach has just been to assert a set of ODEs based on some kind of loose argumentation about what should be a smaller dimensional set of ODEs that captures this behaviour. So like I say, for the most general Tij, this is kind of doomed, right? Because you can always dream up some discrete structure where this doesn't work. And a lot of the kind of moment closures or ways of writing down small numbers of ODEs have worked very well for kind of different systems of interest. But my main kind of, well, I want to be the take-home message is we can do a bit better than that now. Right? And the kind of the three key places where I think there's been reasonable progress is on loopless networks with heterogeneous degree, clump-based models, and more general kinds of clustering. And it's only for the latter one where now it's kind of still a bit of hand waving rather than a kind of really clear route through. But I think we can do a bit better at explaining why more general kinds of clustering when the approximation will and won't work. Okay. Okay, so the configuration model. So it's a bit disputed who really wrote this down, because I guess kind of Balabash and other people sort of knew things about heterogeneous random graphs quite early on. Then sometimes people cite Mollo Reed, and so on. So exactly who should get attribution for this, I'm never quite sure. And the way I think about it, and I think epidemiologists have ended up thinking about it, is really kind of something that random graphs people have only really done recently, which is thinking about generating this via a stochastic process. So I'll start by defining the stochastic process rather than all this kind of historic stuff. So you start by giving everyone a number of stubs, ki, that's at time 0. And you might, for example, do this by picking ki from a distribution D. And in this case, let's see, write the probability mass function of that distribution. And the probability generating function associated with D is then the sum over all degrees that you can take times the probability of that degree and x to the k. So those are things that turn out to be useful. And there is a difference between just allocating everyone a stub, a number of stubs, to say there'll be 1, 1, 1, 1, 1, 3, 3, 3, 4, 4, 4, and actually specifying a whole set of numbers and picking from a distribution. So in theory they're different, but for epidemiological purposes they're not really. So we might as well always assume that you've kind of picked from a distribution. But if you want to be very very careful, and particularly in the case where there's a lot of heterogeneity, that distinction stops being quite so pedantic, actually. If we're really measuring these kind of extreme power laws, I think it's still an open question exactly how you really capture full-on power law behaviour, if we think that is there in nature.
But I guess the difference is where you take expectations at some point, not so much on the result, but if you take expectations or not over the distribution.
No, not at all, no. Actually, it's a combinatorial issue that you just can't, if you've made some very big picks, you just can't link them up into a graph. And that becomes more of an issue.
It depends a bit if you're interested in the mean behaviour. If you're interested in the variance, then of an epidemic, then this difference does matter.
I think if you really want to assert a given network model and think that people are linked up in a certain way and they report certain numbers of contact, there are certain sets of numbers that you just can't link up into a network. And that's unimportant if the moments of your distribution are all finite. But if any of the moments starts diverging, it can become quite difficult to actually link up. But that's a combinatorial point that I think I don't think it is just an order 1 over m. But could discuss later, so hopefully I'll provoke some.
Okay, but this has to do with the construction of the underlying graph.
Yes.
Either it's 100% feasible or 99% feasible, depending on the distribution you want for the degrees.
Yes, but some distributions it's kind of getting to like 50, 30%, so you actually have to throw away lots. And the reason I think that this kind of thing can be worth thinking about is it provokes other scientific questions, right? That if you measure something somewhere, people report these very heterogeneous distributions of degree, and you couldn't link it up, well, that should in theory be a spur for further investigation. But for negative binomials and other things, then I think it isn't of epidemiological significance, that distinction. Okay, and then run a process where okay, you also start with, that's step 1. So you we're going to build a network of connections. And the idea is that the stubs kind of pair off with each other. Okay, so the idea is you go into the market for network connections with a certain number of stubs, and the stubs link up with each other homogeneously. So I quite like this dynamical interpretation because it probably is quite a sensible way of thinking about how people might form networks, right? Particularly, perhaps like a drug-using or sexual network, you might have it might be a model if you're having a demand for a certain amount of behaviour, and finding other people who have a similar, putting a call out for a certain number of behaviours and linking up. And then when you think about it like that, it makes it clear why it's not a particularly sensible, or why it's probably a falsified model for formation of networks relevant for these kinds of heterogeneous behaviour, because it's too homogeneous, right? So that you've put in some heterogeneity at the start, but the way in which that heterogeneity is linked up is then too homogeneous. So there are generalisations of this and so on, but that's the note of caution. But the big positive is you can do quite a lot analytically. Anyway, but doing this leads to things like self-edges, and a whole load of other things that are not desirable in a graph, but maybe don't matter too much if you were just prepared to do this. And really, all of these things are kind of order are really order 1 over m, provided the distribution's nice. And this makes the configuration model kind of a sensible. If we try and put ourselves into this large n regime, that makes it a kind of good thing to start with. Okay. So then if you start like this, I'd say that, again, this is a kind of personal way of thinking about it. So Frank and Pete didn't write their argument out like this. But suppose you thought about this way of making a configuration model and the epidemic process that we had up there. Which I'll call star. And ran them at the same time. So the individuals are, so you've got a susceptible individual here who's got ki stubs left, an infectious one who's got kj stubs left, and you've still got the network that you're making. Although you'll see this doesn't particularly matter. And at the same time that these two guys pair up to make the network link, the infection's transmitted across. And then there are a load of other events and rates that you have to take account of to kind of really embed these together. But I think this kind of one's the important one. That's that as you're making these, yep.
Sorry, I realise I'm not being a bit stupid, but could you take me through what you mean by the notation of putting the thing in the back of the thing? So what you're saying?
So it's because if you really wanted to write every kind of random variable out, it would be tricky. But this means that so Markov chain can be defined in terms of events and rates, and an event is this random variable changing state by removing its number of, it's a random variable for the number of states, so it has a probability, but that probability isn't dependent of a load of other probabilities. So an easier way so you can try and write out equations for all those probabilities, which is the natural way you start thinking about simple stochastic processes, but that very quickly becomes notationally almost impossible. So this notation is a way of saying, well, what there really are events and rates of those events happening. And this is an event where node I and node j, or individual I and individual j, they each reduce their number of stubs by 1. I changes infectious state, and you record a link on the network. So before we were making the network by the stubs bashing into each other, reducing by 1 and making a link.
Making the graphs like this makes the mixing kind of preferential in Anderson. Higher degree things connecting higher degree things, etc. Is there any idea about what kind of measure that is on the space of possible graphs? I mean, it's not a uniform measure on the space of
So there's
even degree graphs.
There's
It's a preferential measure on the space of graphs. So.
There's a nice paper by Tom Coolan about this, actually, and he comes up with this graph mobility, which is that yes, it's a funny measure, even accounting for isometries and other kinds of. So, the definitive answer to that is in a paper by Anton Coolan at King's.
On the previous blackboard, you were going through a process I sort of recognised of just creating a graph with a chosen degree distribution. So you first choose the degrees of each node, and then you put in the links, possibly refusing to put in self-edges or whatever. But we've now seemed to have moved on to where we're running the epidemic at the same time.
Yep.
And I'm left a little bit confused about how that's going to work out.
Well, so it's Frank and Pete's real insight that the argument is that this is equivalent to running what I called star there on I guess you have to include some kind of correction for large M. But it's kind of equivalent up to large N corrections to
First make the graph and then the epidemic.
and it's because they're both so kind of Poissonian type processes. So what you mean by equivalent, you might have to be careful about. I mean, maybe Frank wants to chip in with whether I've misunderstood the.
No, I think it's generally right. If you imagine doing your configuration model, you start off with one.
Yeah.
You don't pair up its edges until it actually tries to make an infection.
Yeah.
When it makes an infection, you decide who it's going to be. You then pair it up.
But are we only doing this, creating edges for infections here?
Well, the way I did it, when the infective dies, you connect up its edges it hasn't infected.
But this is similar to other arguments in graphs. It gives you the kind of probably same final size, right? And the temporal development is completely different.
No, I think the temporal development is the same.
Yeah.
Same.
Yeah.
Yeah, I mean, you keep track of the number of edges, number of nodes with a different, we call effective degrees, which is the number of edges that haven't yet been paired up. And then when you do the pairing up, because this is just uniformly at random, you can just pick amongst those as you're remaining. You don't actually have to do it all at the beginning.
Okay.
That's a basic idea.
Probably an equivalent way of seeing it is that you create your configuration model at the beginning, but then completely before running the epidemic, and then you keep track for every node which one of the edges has been used to transmit the infection, and you imagine that edge gets.
No, I think, Lawrence, I think I can see exactly what you're trying to do. I just wasn't clear to me that this was the formalism that corresponded to it.
But again, I think as well as this being a mathematical trick, the thing I would broadcast is it's quite an attractive picture to have in your mind, right? That somehow this picture of stubs or demand for risky activity, I think is something a bit like what people carry around, right? People, either your job requires that you speak to a certain number of people, or you're kind of, you're going to want to inject a certain number of needles of heroin to support your level of addiction, or this kind of thing. And so thinking about how those kind of stubs pair up is I think, quite an attractive general approach epidemiologically. And so, and it turns out that if you assert that as your initial model, it's quite easy to start writing down differential equations without necessarily having to worry too much about the argumentation. Anyway, so these de Cruz-Von et al., Vietran, can't remember who else was on the paper, they kind of proved convergence using a really, really tricky argument. And Malvina, who was here in the first week, just had out a kind of slightly simpler argument for why so these equations by Eric, and these equations are kind of a bit like pairwise equations, but you have this. In these equations, there's an idea that your probability of remaining susceptible, given that you've got degree k, ought to go like some other parameter to the k. So somehow what Eric calls geometric scaling of risk with degree. And again, I guess I've thought about this so many times it's become quite intuitive to me as a way of thinking about it, but it's probably worth digesting. This is the main insight, that if these links are all pairing up at random, then each link carries with it an equal and independent risk of infection being transmitted to you. So you just multiply up those independent risks, and 1 minus the risk is theta. So theta is the probability that any one of your risky behaviours, which are assumed to be independent in this model, unrealistically, as I'll come on to say, each one of those has a kind of probability of remaining safe.
Convergence to what? So
There's just a set of ODEs which I'm just about to write down.
It's a function of time here.
Yes. Yeah. So theta is a monotone decreasing function of time, because you start off with theta quite close to 1, and then it goes down to. So in fact,
Doesn't this mean that you are throwing out the idea of local diffusion of the settlements?
No, not at all. So it's very important to note that the low, this really accounts correctly for the low degree nodes, the people of degree 1, somehow being a dead end, and they don't get to push the infection back out into the network. So that's the main thing it gets right compared to the people who throw that out. So you kind of in the Vespiniani and Pastor Sartoris model, they throw out the local depletion, but this really does get local depletion. It doesn't get local dependence. It doesn't get transitivity, and the fact that you're probably part of a group. But it does get the heterogeneity absolutely right in that the people who are degree 1. As an example of why it's wrong, right, a configuration graph that's heterogeneous will tend to look quite a lot like a tree. So you might have the kind of higher degree nodes in the middle and the degree 1 people on the edge. Okay, so it captures correctly that you've got some people who are low risk, but what's really happening in, say, a sexually transmitted network is you'll have a lot of pairs, and they're quite perhaps distinct from the core risk group, and they're, so you will have some pairs that are completely split off, and the configuration model doesn't really generate enough of these monogamous pairs not connected to the. So you want some extra kind of preference and group membership or something. But it's a starting point, right, for really getting the fact that these people on the edge really don't push it back into the network. So it's an advance, right? Not everything that you'd want. Okay. Okay, so this is notation which I think is really ugly, but we're kind of stuck with how you keep track of the kind of macro properties of these kind of dynamics on a network. So some work that I did recently was thinking about, as it turns out, the Volz equations. Well, actually, I won't quite write them down because it turns out that this kind of nice trick that lets you write down just 4 ODEs, or in Joel Miller's formulation 1 ODE, is really kind of, as you might expect, a very special trick and doesn't always or kind of breaks very quickly. But something that you can always write down. Now this is if you're on a graph where it is just a graph that's kind of 1s and 0s and a rate. So it's if we're in so we're assuming this here for the interaction pattern for any graph, for any G. So yeah, we're assuming Tij is Tor Gij. So for any G, you can always write this. And this turns out to be exact in the kind of limit of very large N, but it's not kind of closed, right? So you don't have to write down equations for the pairs here, and the pairs all depend on kind of triples and higher order structure in the network. But so recent work I did was looking at the noise in this kind of process. So you can think about this ODE limit and actually write down a closed set of equations where you have a kind of noise term here that turns out to depend on this kind of per link risk parameter theta, as well as the number of people infected, and then just a finite number of pair variables. And you need 4 ODEs. You need 4 stochastic differential equations. You need a stochastic differential equation for each of these. And what this lets you do, you get the standard result out of this set of so mean I goes like ETRT for R. So this little g is the probability generating function of the degree distribution. which is just a quick way of writing the moment. So the double prime means it goes like the second moment, basically, of the degree distribution. And it turns out that then the variance in I over the mean in I squared, that asymptotes onto something that's quite a complex formula, but it's a big formula with lots of terms in it that I won't write the full thing out. But we were able to get an asymptotic expression for the variance in growth, and it depends on the third moment of the distribution of degree.
At any time point t, or the variance of r.
Early growth. So this is asymptotic early growth, and so what you find is that if you take log of prevalence against time, so epidemics look like this. They look a bit like, so almost any epidemic looks a bit like two Laplacians, but with a round off at the top. Right? And it's that during this bit you have a kind of envelope of noise, and the kind of width of that envelope is determined by the third moment of the degree distribution. So Peter was mentioning in a few of the discussions that there are these results that kind of whatever any kind of power law distribution of degree allows some probability of an epidemic persisting. Right? And I think this is perhaps a bit related to that, although we couldn't prove it for power laws. Just generally, that if any moment of your degree distribution really does diverge, then there's going to be something funny happens in the stochastic model, and an epidemic's always going to have some probability of taking off. Because you can imagine that even if you expect your growth to be very slow, if this variance is also divergent, there'll be some fluctuations that kind of push you. This is a kind of hand-waving argument, right, with mathematicians, but I think intuitively there's this thing that having divergence, if we really are measuring power laws, that ought to give some very funny epidemic dynamics. And again, I think that should be a spur to thinking carefully about, and it may be just something as simple as if you meet an awful lot of people and each connection is then less epidemiologically significant, right? That might take all of this effects away, but then it may be very important to include that in models, right, and ensure that we don't take the power laws too literally.
If you have a broadcasting server that connects to everybody, there's something funny will happen with the epidemic.
But it's a general observation.
Infinite mean and stuff like that.
But it's certainly a general observation that epidemics are noisier than the simplest models of noise predict. And so this is saying, well, if you've got some heterogeneity in the population of it, you've got more noise. So I think it's at least part of the explanation as well for this observation that an epidemic curve is typically a lot wobblier than, some of that's reporting, but I think some of it is just that the underlying, I would guess that almost anything that isn't homogeneous mixing is noisier than homogeneous mixing. That's my guess. If you hold R constant, if you hold the early growth constant. And so I think that's something that may help to explain why observed data are so noisy compared to the kind of nice smooth ODEs, right? Because I think we are in the ODE limit quite frequently, or in the SDE limit, but the kind of general oscillations ought to be a lot bigger than the simple diffusions would predict. Okay. So households is another thing where something can be done, and households really, there are these worries about how heterogeneous are heterogeneous populations, but we all really do live in households. So I think it's quite easy to motivate that we can go and measure this, and they throw out not so many paradoxes as well. So we start with the system start.
There's something, to translate it back to probability.
Yeah.
Probability, you have this space of possible graphs with a certain property, say degree distribution. And then you take them all large, and then you seed them with sufficiently many first infectives to have some kind of epidemic, because here there's no probability of no epidemic. Then, for instance, there might be exponential. The question is, with probability 1 on this space, you have exponential growth on all of them. And is it the same R on all of them? This is a kind of average R, I guess, that has been computed, right? You must have a distributor, or is the result that there is only one R in the limit for all these graphs?
I think the measure of ones where R is not. Let's see, what's the convergence?
No, because from a practical point of view, you would be interested in that, right? If we believe that we live in one of these graphs, then we would like to know, is there a definite R for diseases, or might there be many depending on something else that is not properly defined by the degree distribution? Because this is the kind of the expected value of the expected values of various things, right? Before you get to this thing, many expected values.
Probably the worst thing about the configuration model is the lack of local structure and the lack of degree-degree correlations, which are now also reasonably, those two things I think reasonably well understood. So the degree-degree correlations is, and they're both I think seen in this picture, that it tends to generate things that look a bit too much like sort of spindly funnels going into a core, when often you want to break more things off and you want the core to be more clustered. So I think it's quite well understood why they'll be wrong. But you can see it already requires quite a lot of argumentation about how to really analyse them correctly. Okay, so actually I think I'll skip through how you define it going from star. You can start with star and you can let so you let individuals be in M households, each of size n. So in this case, big N is M times M. And then in the same way that you can kind of, if you want to put limit theorems, invoke limit theorems or be careful, you can kind of carefully argue through that you'll get a set of differential equations for and so this is the proportion of households with X susceptibles and Y infecteds. And so you can get this very large set of ODEs. So it's still an improvement on the kind of exact dynamics in terms of dimensionality.
So the households are some fixed size, and the number of households is thought of as large.
Yes. So you get so this IT is sum over X and Y of Y. So that's the total amount of infection in the system. And so you get this set of ODEs, which isn't too bad. It goes like n squared rather than, it goes like little n squared. And what that does is let you work out what's going on in all of the households as you go through this epidemic. And actually what you see is, actually if you follow them through, you get quite a nice pattern where so this is kind of just the marginal on P of Y. So if you sum over the X's, you start off with most households having none. And then as the epidemic grows, you see a kind of nice thing that looks a bit like a binomial going up and down through the households when you solve those ODEs. But you always pick up a kind of decreasing probability here. So I guess this starts off bold and gets of some households sort of not getting any infection in them. So it evolves that kind of set of proportions, not really probabilities, because you've thought of lots of the household. But one thing that kind of sort of challenge that one might want to rise to is, well, that is still quite a lot of ODEs, so can we get any smaller? Because what a household graph looks like, if you want to interpret that picture as a network, is basically a load of little cliques, and they're connected by these long-range links. So it's quite a lot like the small worlds type picture, right? You have a lot of local clustering and a relatively small number of long-range links between the clusters. So you have short path lengths. It's easy to get from clump to clump, but a high clustering coefficient. And so being able to write down a small number of ODEs is good, right? That's the idea of moment closure, is you're trying to go from the stochastic system to a relatively small number of ODEs. Well, one might argue that's still quite a lot of ODEs. Right? So can we get smaller than that? And it turns out that if you manipulate that set of equations there, what you get is so I'm writing P with the underline for a kind of vector formed of those elements P. So you somehow spread out that matrix into a vector, and the form of the equations you get looks like this, which isn't much better because you don't know what P is. So I scratched my head for a bit, and then it turns out that if you think about writing the equation for this P as a matrix equation, then there is actually a body of theory that tells you how you can solve this in terms of something that isn't a differential equation. So there's an algebraic theory, and it turns out that you can then approximate in a kind of principled way this as a matrix exponential. Where so you need to add one ODE, and then this is an algebraic expression here, and then there's some other corrections here. But these corrections form part of a series that you can kind of define extra terms in, for as long as you want to get convergence. So it actually turns out you can do this in 3 ODEs. And let's see, Peter Dodd.
That means that you assume that H in function is dominated with an I then. To have that kind of, I mean, there must be some.
Yes, it doesn't always.
The components, if you want to do this linear approximation,
doesn't always converge. Yeah, you have to check that it converges. So it can converge. Yeah, doesn't always. So this is work that I just submitted. But it's a bit similar to previous work, it's Dodd and Ferguson. And they got it down to 2 ODEs and an integral, or an integral differential equation. So my approach is just differential equations. But this idea that somehow even the household model is too much, and you want to know what you can do in a system where there are lots of short closed loops, without just by brute force doing all the ODEs for the loops. So maybe algebra will be a solution, but I'm not promising it. I'm just saying that that's one set of approaches to trying to avoid just enumerating all of the dynamics in cliques.
That's the practical question. Since you probably try to solve these household equations, you have a system for generating them automatically. So, because otherwise you have to write them all down. There are many partitions.
Yeah.
You succeed in writing it automatically.
Yeah, you can download it
or something.
epistructs.sourceforge.com. If you want to play with these, actually, yeah, please play with these. If you look up epistructs on SourceForge, if you want to, there's MATLAB code that generates these kind of ODEs and does some other things that you can do with them. Yep. Yeah. If you want to implement it in something else, great. Okay. So those are 2 regimes where we've got a chance of doing something exactly right. You've got local clumps, all the clustering stuck in local clumps, or just kind of purely global mixing of some sort. And you can imagine generalizing that, right? So you could consider a model of clumps, but where the global links weren't just completely random, where the global links were a configuration model. That was kind of Frank, Peter and Dave Searle thought about those kind of models. So you can imagine variations on a theme for these 2 approaches to networks, and that would let you write down a set of differential equations that would capture the kind of middling behavior of an epidemic. But there's always going to be this issue that that network is not going to be an accurate representation of reality. And so I'm going to propose a kind of sidestep. Right? The final thing I wanted to say is propose a sort of sidestep to that problem. So suppose you start with, so you don't worry about the noise that we had trying to close, but you start with this equation here, and then write down the next okay. So you can keep going, right? You can then write down equations for the triples, and I've had a look at that, and it's quite pretty if you like playing with little graphs. But it quickly becomes extremely tiresome. And so most people think that you want to kind of close at this stage and just keep track of the pairs. And so the paper of Matt's is often cited. People often cite also Kirkwood and Boggs, but I've not been able to find a PDF of this paper. I just know that people who have found the PDF have thought it's appropriate to cite it. So I think it's probably nice to call it the Kirkwood closure. And it's kind of got this intuitive form where you say, well, a line, an ABC line like this, a triple. So I'll just explain this. This is one at the top here. It's saying that where you have SI pairs on a network, they're created because an I infects an S. They're depleted because an I infects an S in one of these. So an I can infect an S in an SS pair. That turns the SS pair into an SI pair. If an I infects the S in an SI pair, it turns them into an II pair and removes them. That's why there's a minus sign. They're depleted by internal infection and by recovery. So that's explained the right-hand side here. And then you might say, well, these triples, either we know that they're linked like this, either they're linked here or they're not. If they're not linked here, then let's kind of look at the pairs and individuals that are in them, well as an AB pair, a BC pair, and then we've overcounted the B if we've producted those two pairs, so let's divide by it. And then you apply that same reasoning when they are connected. You say, well, suppose they are connected. We notice there's another AC pair, but then we've overcounted an AB and C nodes, so let's divide through by them. That works very well. So Dennis showed the pictures during the space discussion. And it doesn't work well for lattices, but it works well for n-regular graphs. With small phi, and somehow the phi should be kind of uncorrelated or random. In practice, introduced by so phi is the clustering coefficient. So phi is just if you count up all the triangles on the network and divide it by all the triples. So it has to be between 0 and 1. And so it works quite well in that case, and works a lot better than it ought to. And no one really knows why. No one knows why it does or doesn't work. It just kind of, but it was applied to real-time foot and mouth analysis by Ferguson and others, and various other applied problems. And I think that shows why people, my initial statement is true that people like ODEs, right? If you're going to do something quick, people are going to want ODE systems. So there's some point in trying to derive and understand these systems for kind of war use. And it's because this phi really does capture what happens when you're, so I talked about in the configuration model, if everything's global, these links are independent. And really what this captures is the rough phenomenology of what happens when the links are non-independent. So when you're, the fact that you've already drawn an I from your neighbourhood means that you're more likely to pick another I because it's likely you're part of a cluster and that infectious person infected someone else in the cluster. That's what this gets. It gets the rough effect that you'd expect that to have, but not in a very principled way. So the problems are, it's not really based on probabilities It doesn't conserve pairs. So it doesn't conserve if you sum over all A and B. It doesn't conserve this quantity, which is problematic. And it has the wrong order epsilon behaviour if early I is given by some small parameter epsilon. It doesn't have the right kind of behaviour in order epsilon if you think about how it ought to. So it has these real problems and works better than it ought to given those. So Matt and I proposed a different approach, which was to notice that, so we introduced a notation where you think about the I kind of coming in on a susceptible, because it turns out all the equations you need to kind of write down a closed set of equations, they all involve, the only time you need to write down a triple is because an I is kind of acting on a susceptible that's part of a pair. And then so we wrote down a closure based on kind of just this seems like a nice thing to write down. But before so I'll write down the one that's a nice thing to write down then. So our approximation was so that bit's unchanged, the unclustered bit, but then if you add some clustering, okay, we really got to this from the last argument there. We were thinking about the order epsilon behaviour in small epsilon, so that was how we wrote it down. But then I did some work with Istvan Kiss and some of his collaborators. We thought about whether there's a kind of nicer interpretation of this. And so suppose you start with an S, and you know that there's one I coming in, and then you want to know what the probability is of another neighbour being B. So this was in the configuration model, we were assuming that this probability was independent of this one. But then suppose you say probability of being B, okay. So I'm going to write P of B slash is PB is BS over NS. And although writing this PB, maybe you say this isn't really a probability, but it's a count of BS pairs over all of the N links that you expect to be coming out of S individuals. So it's a proportion, I guess. And then there's a correlation term that you can define between being B and being I, which is again a kind of natural way of thinking about what correlations do exist on the network in general. Okay. So then you could write this as it's a probability that it's not linked to the... So if you assume that phi is an independent probability of it linking to the I or not, you can say, well, if it's not linked to the I, they can't be causally connected. And so the probability is just PB. It's just the probability that the proportion of randomly selected B's around an S, because there's no other communication that can go on. But if there is a link, which we assume happens with probability phi, maybe I'll treat myself to some colour to show that. Okay, and that normalisation is just to make sure the whole thing's a probability distribution. And this has an interpretation in terms of non-independent Bernoulli trials. So what you're doing is really explicitly saying there's some process going on that means that picking i's as I kind of go around the different neighbours of this S is non-independent. And so this is what I'm kind of proposing as a sidestep really to these problems about network topology. So if you assert this model anyway, I'll say one of the final thing I'll draw up. So suppose you take an SIS process with contact tracing. So individuals go S to I, they go I into a tracing class, and then back to S. And while they're being traced, you're kind of trying to mop up their I's and move them into the tracing class. And if you run a load of Monte Carlo simulations for this on a clustered network, you get some kind of envelope going to. And if you write down to some standard ODEs without any kind of pair structure, what happens is you predict a trajectory a bit like this, so something very wrong. If you write down the Kirkwood approach, it kind of still gets the kind of asymptotic, it gets the kind of stability of this one wrong because it thinks there's an imaginary component on in the Jacobian, but the kind of improved one, I think, almost entirely just because it's a probability distribution, so it does something sensible, really does follow the simulations a lot better. And capturing contact tracing in ODEs has been one of these kind of problems, right? Something that would be nice to do. And I think we've kind of cracked it in a sense, right, by saying you can at least write it down. So my proposed sidestep is in a sense to say, well, if you can't solve it for an exact topology, maybe we can at least capture some of the phenomena that we would expect that topology to impose, like non-independence of links around a susceptible. And so maybe one route forward is just to assert a different stochastic model that isn't necessarily tied to an explicit topology, but just includes some measure of clustering or assortativity that you could then fit to data and say, well, does this, as just a different stochastic process, does this capture what we're seeing in the epidemic data? And my feeling is that this is kind of quite important, right? Because suppose quite a lot of people will look at your epidemic curves or time series and fit some ODE model or model in diffusion to it and compare models. Now, so here's a model with a latent class or asymptomatic infections or whatever, and it fits this time series better. But if you know that the underlying network structure capture is also something that affects the time series, do you really know that your time series has identified asymptomatic infections, or may it have identified something to do with clustering or assortativity? So I think if people are going to try and make assumptions based on time series, it would be nice if there were also ODE models where they could say, could this phenomenon that I'm attributing to asymptomatics or to some other compartmental structure could be to do with contact structure, but for a simpler set of disease classes. And we're not quite there yet. I think it's true we're not there in terms of being able to say, here's just a way of putting your set of compartments into, adding a few more ODEs and seeing what contact structure would do. But I think we're closer than we were when people were just asserting, here's a closure. I think there's a better understanding. And so, very final point is you should ask Lorenzo about his. Lorenzo's been looking at triangles, so just triangles, with nothing else, no other contacts, and looking at these different ways of closing the probabilities, right, and really working out which one's right. And the kind of the spoiler for that, spoiler alert, is that it all, if you're in a fixed recovery situation, everything works really well. And so it's something that the kind of reason that existing closures don't work is because of variability in the recovery time distribution. And I think that's quite a big insight, because before no one had really known why these things do and don't work. And now I think, thanks to Lorenzo, we do know that that's the source of it, right? So we can start digging for improvements. So I managed to get it all in an hour. Thanks for your time. Whoever says it now is going to get a laugh, whatever they say. There's been that amount of space. Okay, right now. Go and have coffee.
We've had a long few weeks.
Before people slip away, can I just make an announcement that there is an email in your inboxes pertaining to the special